Yeah, so I think as Ferenc was just showing, what we did last term for machine learning in the physical world was we set up a Reddit forum. And this, what we like about this is that this gives us a place where you can ask questions, and some of you who have answers can help answer those questions. So Carl Henrik is the only one of us who we know who's got sufficient kudos on Reddit to set up a forum. That's why it's set up by him. You can check, I'll send a link in the chat for the ML and the physical world in a moment, so that you can see the sort of conversations people had on that forum. But the idea is that this can be a nice place where you can ask questions and questions can get uplifted, and we can see where misunderstandings are a bit more flexible than what Moodle provides. And of course, you can post anonymously on this. So if you're embarrassed about your question or whatever, you can put it up anonymously, and we've got no problem with that. You shouldn't be embarrassed about any questions, though, to be honest.
Yeah, I should also note that this is all public if it's not clear to everybody. So
yeah,
this means that hopefully we're not going to get a lot of people. Not going to get this subreddit swamped by outside people who are not actually part of this course. But it should be, just be aware that everything here is going to be publicly visible in theory by anyone.
Yeah, that's a good point. Thanks, Ferenc. So unless there's other questions, so just been asked if I had the diff for the errors. Yes, this repo is public, so you can actually fork the whole course if you are interested in doing so. I'm gonna, at the moment, Ferenc's slides aren't integrated in the way that mine are, but that's something I'll work on this afternoon, and the notebook. So you can see the diffs through that fork. It's going to be a bit hard to see because it's HTML, but there you go. But so without further ado, Ferenc.
That's me. Hello.
So by the way, I'm gonna, Nick and well, certainly I will, and if Nick, if he fancies it, we're going to do chatting commentary in the chat. So if you open your chat, hopefully it won't distract you. Ignore it if it's distracting. If there's anything we think helps clarify, we'll try and write it in the chat. Off you go, friends.
Yeah. Also, feel free to stop me if you actually have a question, or if you notice a question that I should stop and answer. So welcome everyone. This is the third lecture in the Deep Neural Networks course. My name is Ferenc. I'm a new lecturer in the department. I joined in June last year, so this is the first time that I'm teaching. This is actually my second lecture, but just, you know, be nice to me, basically, is my my point here. And today I'm going to do two things. So the first half roughly is going to be follow up on the generalization points that Neil started to introduce or introduced in the last lecture, and I'm just going to follow up with it, follow up with some of my own views on generalization in neural networks and why neural networks work so well, or in what sense do they work so well. And then in the second half, I'm going to start talking about optimization, which is what the on the schedule, the original topics for what these next two lectures are going to be about. And today I'm going to focus on how do we calculate gradients, which is actually like a fairly general topic. And the second lecture, which is next Tuesday, I'm going to talk about stochastic gradient descent, which is much more deep learning specific. So connecting back to what we talked about last time, I wanted to talk a little bit about approximation with neural networks. And here, approximation theory generally is about the question of what sorts of functions can we model with the models that we choose, or with neural networks in particular here. Neil has shown examples of nth order polynomials, and we've seen examples of what kind of functions that results in. So it's kind of interesting to think about what these deep neural networks actually look like, or what sort of functions we can or cannot model with them. And for this, I'm just going to assume the most basic form of a neural network. You've seen this before, I think, in one of the slides, and I'm pretty sure that you've seen it in other contexts. Most of you have. The basic multi-layer perceptron, which has capital L layers, and for each layer, each layer's output, f of L, is some nonlinear function of a linear function of the previous layer's output. And I define f0 to be the same as the input. So x is the input to the network. I'm in every layer, I'm multiplying that by a matrix W. I add a little bit of bias, which is just a constant to each of the dimensions. And I apply this nonlinearity pointwise. So for each, this is going to end up a vector, or in general a tensor. And I apply this nonlinear function to each coordinate of that vector. Sorry about this. We can also write this in this expanded form, where it becomes obvious that we are talking about a function of a function of a function of a function. So I just substituted fl minus 1, and then I substituted fl minus 2, and so on. So we get an expression like this. And I guess from this point on, in this world of multi-layer perceptrons, the big difference is how do we choose this nonlinearity phi here. And this is just a single scalar function. It has a scalar input and a scalar output, and it applies to each dimension independently. And the tool that we most often use nowadays in deep learning is this very simple nonlinearity in many ways. This is called a rectified linear unit, which for its input x, it returns 0 if the output is less than or equal to 0. And it returns x if x is positive. And it looks like this. Sorry, the axis labels are not going to show very well on these slides. I will try to fix them, but hopefully you will see some of it. And it's not terribly relevant here. But you can see that for positive values, it's essentially the identity function. And for negative values, it's 0. So the interesting question that I wanted to look into a little bit today, not in a lot of depth, is what kind of functions can we represent with these nonlinearities? And the first thing that I looked at, and I have this Google Colab notebook where you can play with this a little bit, is a single layer, a single hidden layer ReLU network. So what I'm going to have here, I will actually show the next slide first. I have a single scalar input, so it's one-dimensional input. I have one hidden layer. I have ReLU nonlinearities, and I have a linear combination of those outputs. What I show here is the activations of each of the units in this first hidden layer after the ReLU has been applied. And because this W can be, it's a vector, generally speaking, you have the activation on the first layer is going to be a vector in this case. And what I'm showing here with different colors is the different components of this vector, and as they respond to different values of the input x. So the x-axis here is x itself, and the y-axis is the ith component of this activation. And for different I, I'm showing for different colors. And you can see they all have the same shape, except that they have their slope at different locations. Some of them might point in the negative direction, and the location of where this kink happens is also at different places. So if you put this together in the single hidden layer network, you essentially multiply this with another vector, which is essentially a linear combination of these functions that I've previously shown. And that's going to result in a piecewise linear function. And I also noted here these the boundaries of these segments, the linear segments, and I color-coded them so that they correspond to the different unit activations that I've shown in the previous slide. So for example, I have a kink here, which is shown by the orange, and that's because there is a unit, the orange unit, which is 0 below this value, and it starts to turn on after that value. And because it starts to turn on here, it's going to change the slope of the output at that location. It's pretty straightforward, I think, how these ReLU networks tend to work. But what's important about this is what happens if I add another unit. If I added another unit, I would add another function of this form, which in the output function would result in taking one of these segments, cutting it to half, and adding another kink to my function. So if I look at the number of times this function changes slope, which I like to call the number of kinks, it actually grows in the order of the width of the network, or the number of units in the network. So if I have 10 units, I will have 10 linear segments. If I add 100 units, I have 100 linear segments. And that's not a particularly good scaling in terms of complexity, because if I want to model very, very elaborate functions, if I want to model them with these kind of linear networks, I will need to change direction a lot of times. So I want to have a lot of these units, and that's sort of the linear scaling property of a single layer neural network. So what I'm going to do next is look at, instead of trying to add more units in the same layer, so trying to make my network wider, what would happen if I tried to make my network deeper? And it turns out it's going to be a much more efficient way of increasing the complexity of this, of the function that I can represent. And what I show here, and again, this is in the Colab notebook, you can play around with it, is a particular example of a function, which is a layerwise function or composite function that you can implement with ReLU networks. And this is what this function does. It's called the sawtooth for reasons that are going to become obvious once I show you the pictures. What's happening here is that F0, as before, is just X. And then every subsequent layer is the absolute value of the previous layer multiplied by 2 and then shifted down by 2. And that's all essentially. And you stack this operation multiple times on itself. And this, of course, can be implemented with ReLUs, because the shape of the ReLU, you can imagine the absolute value looks like this. If you can see my hands, the ReLU looks like just 1/2 of the absolute value. So if you put two of them together, you can obviously model the absolute value function with it. So here I'm showing, not sure yet, I can't see because of my own picture, what's on the right-hand side of the slides. So, I could replace the absolute value with ReLUs, and this is perfectly implementable with a ReLU network. And this is a multi-layer ReLU neural network with fixed weights. So I told the network what weights it should have, and it has 2 ReLU units at each layer. So it's actually a very, very small neural network. And let's look at what happens as I look at the activation, so this FL function, as I increase L, the number of layers. This is a 0-layer network, which is F0. So on this is essentially just the input. We see that this is obviously the identity function, nothing interesting to see here. So what happens when I first apply this layer is that I get something that looks like the absolute value, because that's what a layer does. But then it's also shifted down. So the important point here is that the minimum of this function is now at -2. So it's absolute value, but it's shifted down so that it sometimes goes to negative. And what happens if I apply this layer another times is that the bit that was negative before, because of the absolute value, now got essentially sort of switched to be positive. And if you look at the number of linear segments, before we had 2 linear segments, and now we have 1, 2, 3, 4 linear segments. And at this point, we added 2 layers, and there are 2 neurons at each layer. So we have 4 units, and we have 4 linear segments. So far, it's nothing particularly interesting. But if I keep doing this, every single time I add a new layer, I actually double the number of linear segments. So this happens at the 3rd layer. You can see that those teeth that were pointing down and were below 0 have now been reflected upwards, and that creates 4 extra segments. So I double the number of linear segments by adding an extra layer, and this is the 4-layer version. And you can obviously keep doing this, and essentially infinitely until you run out of numerical precision. So what's interesting here is if you count, this is now 32 different linear segments. And I achieved this with a 5-layer network, which has 10 units in total. And in this specific example of a ReLU neural network, we can see that the number of kinks, or the number of linear segments, grows exponentially with the depth of the network. So adding more depth to my network buys me much more in terms of the representational power of these ReLU networks. And this happens not just in 1D, in the 1D example. This happens in in multiple dimensions, except that you're no longer looking at just kinks in piecewise linear functions, but each of these ReLU units is essentially defining a half space. So for example, this unit acts on a 2-dimensional space, and say the green bit is where its activation is 0, and in the lighter green bit, its activation is slowly increasing. The way this image is color-coded is that it color codes the different linear regions differently. So it's not a heat map, it's just color coding that this region here behaves differently from how the other region behaves. And if I have a single network or a single unit, it essentially cuts space in half. And if I add multiple layers, then you can have these more intricate behaviors for each of the units, where the different regions of the space are going to behave very, very differently. And this is an actual illustration of what happens in a trained neural network. I think this was trained on MNIST, which is one of the basic toy examples now in deep learning. And as you look at a 2-dimensional subspace of the input data, which would be a hand-drawn image of a hand-drawn digit, as you change these 2 dimensions, this picture shows you that the function estimator is made up of lots and lots of little segments. Within each of these segments, the function behaves linearly. And this particular picture, I like it because it looks very cool, I think, but it's a little bit misleading because it seems to imply that the function that we are getting is not continuous. But in fact, it is continuous. So all of these little regions, the function is linear within, but these linear segments that are neighboring fit together seamlessly in a continuous fashion. So you still define this nice continuous function. It's just made up of individually linear places or linear little shapes. So the summary of this is that depth increases model complexity, which is essentially the richness of the function class that can be implemented with these networks. Depth increases it more than adding width to the function does. And as a consequence, if you have, even for moderate depth, so something like 5 or 6 layer networks with lots of parameters in each layer, the model class defined by deep networks is actually very, very large. And from the perspective of approximation, this is great because now we can represent all sorts of weird behaviors with these functions. But it's also a cause of concern. And this is one of the reasons why people expected that neural networks shouldn't really work, or they won't work. Like very big neural networks simply define a function class that's too complex. And if you recall Neil's lecture on Tuesday, he showed you these nth order polynomials. And if you add more and more complexity to that model class by higher and higher order polynomials, you could see that even though you could fit your data, training data perfectly, those polynomials don't generally produce good results. They are too complex and they don't generalize well to test situations. And the mantra has been that complex models don't generalize. So you should always try to find ways in which to reduce the complexity of these models. That said, deep learning was somehow, in a surprising way, even though it is a very large model class, sorry about the typo, I just noticed there are probably many more. Even though it defines this enormous model class, it does seem to generalize very well in practice. And it generalizes well, even sometimes without explicit regularization. So the next thing I wanted to talk a little bit about is generalization and how it can be that, despite this large model class, deep networks seem to be doing pretty well. This is the traditional view on generalization. Here I'm showing a model class. So this ellipsis is essentially the class of all functions that you can represent with your parameters. And what we really care about, as Neil also mentioned, is finding models that achieve good risk. So in other words, we are trying to locate within this model class those models or one of those models that also tends to work well in some test situation, which means that if you average the loss, prediction loss on the on some test distribution, you get generally a low average error. And the way we do this in machine learning is by generating a training set and then finding the model that fits that training set the best. And what I'm showing here with the green star is the model within this big model class that happened to be the best on the training set. And the way we reasoned about generalization is that what you essentially want to ensure is that this green star happens to be inside the purple ellipsis or the purple set. And the types of guarantees that we had from learning theory, statistical learning theory, and the theory of generalization said that if your model class is small enough, and if you have sufficient amount of data, then there were guarantees that whatever performed best on your training set is also going to perform reasonably well on the test set, so that the green star is going to be inside the purple circle. And the larger the model class was in terms of richness of the model class, the more data you needed in order for these guarantees to hold. And so if you apply these classical generalization theories to deep neural networks with lots of parameters, they basically say that you need way too much data. Even compared to the amount of data we now use, these methods were just predicted to be absolutely impractical methods because of these generalization properties. So what happens differently in neural nets? I think this is sort of my view or my understanding is that instead of just having a single best model on the training set, in deep neural networks, when the model class is very rich, you actually have a lot of different neural networks that all do really well on the training loss. So instead of a single star, I now have this big set of possible parameter configurations that are going to essentially do indistinguishably good on my training set. And so if you wanted to ensure that this green circle or this green set is contained within the purple set, that's not going to happen. In fact, we know that it is possible to find a neural network for any particular training set test set combination. I can find within the class of neural networks a parameterization that does incredibly well on the training set, so say 0 training error, and it does really, really poorly, arbitrarily poorly on the test set. So we know that there are lots and lots of parameters that fall within this region. So we cannot guarantee that if we end up within the green circle, we also are going to end up in the purple circle, which would have been the classical reasoning about generalization. So what instead tends to happen is that even though all of these solutions within this green set are optimal on the training set, we don't tend to find all of them. If you randomly initialize your parameters, set them to a random value, and then you see where your neural network weights converge to during training, let's say each of these dots represents one of those different random initializations, you're not going to find uniformly randomly one of these possible good solutions. The algorithm itself has a bias towards miraculously, due to factors that we don't completely understand, I think, today, there is a tendency that the stochastic gradient descent algorithm, SGD, will find solutions among the ones that do well on the training loss that also tend to generalize well. And so the new thing in deep learning, in terms of generalization theory, is that previously we only reasoned about the model and about the loss function and its minimum. And now it turns out that if you really want to understand what's going on here, we have to reason about the model class, the loss function, as well as the specific properties of the algorithm that are used to find the particular minima that are actually found in the optimization. So the classical view was that it's about the model class and the loss function. And because deep learning has very big model class, we thought that it's not going to work. And the new model is that the optimization algorithm is also important. So despite the very complex model class, optimization provides some helpful properties that make it work despite the large model class. So I just wanted to put a few pointers up, and I think these appeared in Neil's lectures and lecture notes as well. These have been insights that the community has generated over the last several years. I think maybe over the last 5 years, we can generally say that about this phenomenon of why deep learning works, even though we expected them not to work. And what's common in all of this new work is that they all tell something about optimization, or most of them tell something about optimization. And these new tools are, well, the first one isn't actually very new, which is it turns out that if you start studying infinitely wide neural networks, so you start putting in the limit of infinitely many units in each layer, at initialization, if you randomly initialize this infinitely many parameters, these neural networks start to behave like much more simple objects, which are called Gaussian processes. And we understand Gaussian processes much better. No one understands Gaussian processes as well as Neil does, I should point out. But this is an interesting limit. You can start saying a lot more about these neural networks in this infinite limit. So that's one of the tools that we have to understand how neural networks work. But this is a relatively old insight. We used to know this, and I think Neil can maybe say the exact the date when the Radford-Neal, or the first result that linked infinitely wide neural networks with Gaussian processes. Do you know when that actually was?
Yeah, early 90s. Radford-Neal's thesis is when it
early
became
90s.
attention to the ML community. Probably other people knew it before then.
Probably, yes. So this is due to the central limit theorem. So probably some people have had a version of this before. What's new in this space is the neural tangent kernel stuff, and I think Neil has said this already. What's interesting is that in this regime of infinitely wide neural network, if you additionally throw in this assumption that you're running gradient descent with very small step sizes, we're going to talk about gradient descent in the next lectures, you can also understand not just these functions when you randomly initialize them, but also how they evolve throughout training, and also what they converge to. And so this is an incredibly valuable new tool for us to understand how these very large neural networks can do something useful. And they don't really explain all the phenomena that we see in finite size neural network, but they tend to be directionally very good. And then other kinds of insights, for example, insights about deep linear models. This is I really like this one. It's a little bit weird. What happens here is that if you look at neural networks without the nonlinearity, this is one way to think about them. In terms of approximation, this is a terrible idea, because if you leave out the nonlinearity from the neural networks, then you're just going to have linear layer on top of linear layer on top of linear layer, and the composition of linear operations is still a linear operation. So deep linear models don't buy you anything in terms of what functions you can represent with them. But interestingly, it turns out that if you try to train these deep linear models, they behave differently. You will find different solutions compared to just training linear models in other ways. So it's another good model. You can call it a model organism or a model problem of understanding in what ways the particular gradient descent algorithms we use in deep learning will give rise to interesting properties in models that we otherwise understand very well, such as linear regression. I should also point out the importance of initialization. So how you randomly set the parameters at initialization seems to be very key. And in fact, I have a friend who, when we were talking about, why deep learning works today, why didn't it work before? His opinion is that initialization, like finding out how to initialize these neural networks well, was actually one of the key achievements that kind of quietly happened. And we never think about this anymore because it's built into the deep learning libraries, but it's actually very, very crucial. And indeed, if you try to build a neural network from very, very ground up and first principles and initialize them poorly, and you try to learn or try to train them, you will find that they're probably not going to work. So the particular initialization schemes that we use are probably incredibly important for making deep learning work. And then finally, we are going to talk about this in next lecture, that in stochastic gradient descent, when you actually train neural networks, in every iteration, you only consider a random subset of your data. And therefore, and you calculate the gradient on top of that. And that means that the gradient is actually noisy. It has some randomness into it due to the fact that you choose a random subset of data. And it turns out that this gradient noise, this randomness in the gradients itself, is a helpful property, that if you decrease it, or if you come up with an optimization algorithm that tries to reduce that gradient noise, often you find that it doesn't work anymore. So all of these things are being investigated right now, and I think our understanding of what the core ingredients are and where the magic sauce really is going to change quite a lot even in the next couple of years, and probably also changed in the last year. I just didn't have time to actually read up on the most recent literature. So I'm going to pause here and see if anyone has any questions, or Neil and Nick has any comments to make. I don't know. Are there any unanswered questions, Nick and Neil?
There is a question that was I mean, we've actually ended up talking about symmetries. I'm not sure how widely interesting that is, but one question that came up, I'm afraid I don't have your, it's annoying the way the university is. So R. Hönig, what's your first name? I'm assuming it's Robert, but I may have that totally wrong. So do wide neural networks have more redundancy than deep networks? I.e., do wide networks have more weight combinations that result in the same function? I think it's a super interesting question, although I haven't fully understood the depth of it, but I just let you answer that. So I'll just say that again, do wide networks have more redundancy than deep networks? I.e., do wide networks have more weight combinations that result in the same function?
So, well, that's a very good question. I don't think that's the case. I think that actually deep neural networks have, this is called a reparametrization property, and I'm going to go back to those, that ReLU, this is the ReLU network. Ignore it, it's not very important what the function is here. But one important thing about the ReLU is that where it's non-zero, it is linear, which means that I can increase this W1, say I can double it. And so the output of the ReLU is going to be double as well. And so if I simultaneously halve or divide W2 by 2, then the two operations cancel each other out. So doubling W1 while simultaneously halving W2 results in no change to the function whatsoever. And this is a very big kind of redundancy in neural networks, that you can change the parameters in many different ways so that the function is essentially the same. And some of this redundancy might happen in the wide neural networks, but I think this happens a lot more when you stack multiple layers together, because then you can combine these reparametrization operations. So you can essentially change your neural network in infinitely many ways in terms of parameters, changing parameters, but without changing what function you implement. But it's still a good question, and I don't know if I know the full answer, which is it depends on what you control for. So given the same number of total units across all layers, is this over-parametrization? Are neural networks more over-parameterized when they are deep or when they are wide? My hunch is that it's when it's deep. But
yeah,
maybe
I gave the same answer, but then I think I did, but you explained it clearer. But that's my intuition too. Yeah.
So yeah, so I think that if I in a wide neural network, if I change the parameter that controls this brown bit, the only way I can compensate for changing this basis function is by putting a basis function exactly where this was, or some sort of have to be able. The only way I can compensate changing this brown unit is if I have another unit which has the kink at exactly the same location, I think. So if I want the function to be exactly the same, I think that a single layer ReLU network is actually quite rigid with random parametrizations. So there is almost a one-to-one mapping between function and parameters there, except for with the exception of this invariance of the two W's interacting multiplicatively. But in deep networks, you can see all sorts of kind of units taking over each other's role. Anyway, I think that's probably a sufficient answer. Thanks for the question. Was there anything else, or maybe a follow-up to this?
I think that was the only one I didn't have covered. There's been some other questions we could look at the end, but I think that was the one where I was also a little bit. I think I gave vaguely the same answer as you, so that's good.
Great. Okay. So the second half of or it's not a half anymore, but the second part of the lecture, I wanted to talk about, or start talking about actually optimization in neural networks and what really happens there. The main thing that happens is that we do gradient-based optimization. And I assume that you will have seen this in various contexts before. We have a loss function that depends on some parameters. Sorry for calling it theta now. I used to call this W. I should probably change this back for consistency. This loss is what appeared already on Neil's slides. This is the empirical loss. I have my function, which is parameterized by this collection of weights and biases, theta here, which I evaluate at each input location xn, and I calculate the loss of which is a function of the prediction of my neural network and the label, the actual real label yn, or the desired output. So this is for supervised learning settings. And the way I'm going to find the theta that minimizes this loss is by running gradient descent. I'm going to talk about this much more next time around, but the basic form of gradient descent is that there is a typo. This should be t plus 1. So theta at the next time step is going to be the previous time step minus some learning rate times the gradient. What I'm going to talk about in the remaining 10 minutes is how do we actually calculate this gradient in deep networks. And I have to figure out how to kill this. The annotation now, clearer drawings. And I'm going to talk about this in much more generality than maybe you would see if people were only just talking about neural networks. So remember that this is what the basic multi-layer perceptron look like in this expanded form. And the only thing that's interesting for this conversation now is that you have this function in function in function type of representation. And what I want to see now is how do I calculate the gradient of this function, of the function's output FL, with respect to, say, this parameter W1 here. And from the perspective of W1, for this conversation, it doesn't really matter what the precise form of this function composition is. I'm going to simplify this and say that I have some parameters W, and what I'm interested in is that I apply the composition of a bunch of functions to it. So first F1, then FL minus 1, then FL. These can be arbitrary functions. And I'm interested in calculating the gradient of the output here, FL, with respect to W. And what are the algorithms that I can use to calculate this? The core thing here, which again is not going to surprise anyone in this course, I think, is that you have to use the chain rule. Whenever you have compositions of different functions, you use the chain rule to calculate gradients. So if you want the derivative of FL, so now bold FL is the output of this whole function evaluated at W. And I want that the gradient of that with respect to W is just the product of these gradients. So the gradient of FL with respect to FL minus 1 times the gradient of FL minus 1 with respect to its inputs, and so on. The interesting question is, assuming that I have calculated these, and these are matrices here. So if F is vector and W is a vector, then each of these things here is going to be a matrix. And the sizes of these matrices may be different depending on the dimensionality of each of these functions from which I compose my overall function. Now I can evaluate this in multiple ways. I can first calculate these two and multiply them together. So now once I have these two multiplied, then I can multiply it with this one, and then carry on going from this side of the equality until finally I have calculated all of this and I multiply it with the final layer's derivative with respect to the penultimate layer's output. Or I can do it the other way around. I can start at the end. I can calculate these two, multiply them together, and then work my way to the front. And I keep multiplying these two together and then multiply the result with this one and so on. Or I can do, I can go, completely arbitrarily. I can start in the middle. Well, putting a parenthesis here doesn't make too much sense, but you can just, pick two random matrices in the middle, multiply them together. Now you're left with one less, a product of one fewer matrices, and then you can pick another two matrices and then do this until you're reduced to a single matrix that you wanted to calculate. And these three approaches have a name. The first one is called forward mode, because you start from the input W and you keep going forward in the direction of how the function compositions are applied to your inputs. This one is called reverse mode because you start from the output and you work your way backwards. And this one is called mixed mode because you're mixing and matching what operations you want to carry out. So interesting algorithmic question is, what's the most efficient way to go about this? So let's look at the cost of using the chain rule in these different ways. If I do forward mode, which is I start from here, the first operation is going to be multiplying a D node by D1 matrix. So D node is the dimensionality of W. D1 is the dimensionality of the output of the first layer, or the first operation F1. And if I multiply that with this Jacobian here, the dimensionality of that is going to be D2, which is the dimensionality of this, by D1, which is the dimensionality of the input of the second layer. So this matrix multiplication has a cost of D0, D node times D1 times D2. And once I have this, I'm left with a D node by D2 matrix. And when I multiply that with this, then I have d naught by d2 by d3 cost for doing that matrix multiplication. And so the size of this matrix that I keep multiplying from the left with these other Jacobians, along one of the dimensions, the size is always going to stay d0. So this sum has a more compact form. I can say that this is the total cost of doing this until I run out of matrices to multiply this with, is d0, which is the dimensionality of the inputs, times the sum of the product of the dimensionalities of the subsequent layers. I can do the same kind of argument for reverse mode. It's very symmetric. Now, instead of having d0, so the one size of the matrix is still constant, but instead of d0 being that constant, now is dl. So this which is the dimensionality of the output of this function that I'm taking the gradient of. And again, now we end up with a formula for the cost, which is dl times, again, the sum of the product of neighboring layers. So this thing, the sum of the product, is roughly the same for the two forward and reverse mode. But here I have the cost depends on the dimensionality of the output of my function. Here, the cost depends principally on the dimensionality of the input to my functions. So which one is more useful for deep learning? And I'm not going to talk about mixed mode because that's too complicated. You can do it in arbitrary ways. In deep learning, we mostly care about taking the gradients of scalar functions. So at the end of the day, what we want to take the gradient of is going to be a scalar loss function, which is the empirical risk. So in this situation, dl, which is the output of the function that I'm taking the gradient of, is in fact going to be 1. And this means that if I have to choose between, say, forward mode and backward mode, reverse mode is better because this dl multiplier is just going to be 1. So my computational cost is way lower if I run this chain rule backwards than if I do the forward mode, where I don't have the luxury of using d capital L, which would be 1. So this is essentially just a little bit of intuition behind why we are doing gradient calculations the way we do in neural networks. In the context reverse mode, automatic differentiation is called backpropagation. So that's when you start from the output of your function and then you keep multiplying the Jacobians, working your way backwards towards the input. And backpropagation is not just an arbitrary algorithm that people came up with for neural networks. It's actually a special case and an application of one of the more fundamental algorithms for how you actually calculate gradients of a composite function. You should also note that even though backprop is more efficient in terms of number of operations, it has higher memory cost than forward propagation. And that's because in order to start multiplying the Jacobians towards the end, you first have to calculate the output of each layer and you have to keep those in memory. And I'm not sure if Nick will cover that in his lectures, but this, generally speaking, backprop has higher memory cost at the cost of way faster execution in general. I have a few more examples here. Maybe instead of going through these, I will just stop and see if there are any questions. And if not, then I can talk about these.
More questions. We've only got a couple of minutes left. So yeah, I thought that was really clear, much clearer than I was. So type questions in chat, or if you want to ask live, just put question and we'll call on you to unmute. There's lots of things in the chat. I'll send you afterwards, friends, to see the sort of things, misleading things I've been saying.
Did you say that everything is just a big Gaussian process?
No, you said that, so I didn't need to. So they started asking, so I started adding. Nick says he's going to expand a bit.
More point in memory of backprop.
Yeah.
Okay. Thanks, Nick. So you can pick some of those details up.
I think one of the things, just while some of you are coming up with questions, that we wanted to mention is we want to give you some hints about what's going to be in the first sheet, because we're only going to formally give it to you at the end of week 3, but so that you're not sort of surprised and it's not a load of work. I think what we're going to what we're suggesting is that certainly some of the questions in Ferentz's Colab notebook are of the nature that you'll see in the sheet. They're not going to be too far removed. So basically, if you have a go at those questions, I think you're going to be sort of 70% of the way there. Would that be a fair enough statement to make, Ferentz, with?
Yeah, so I included, like I have this, the example with the sawtooth net example, and I have some questions towards the end. So if you start thinking about those questions, I'm very likely going to base my questions on some of that.
Another question from Keverly, which is, can we share the chat scram? No, I can't speak. The chat transcript. That's surprisingly difficult to say. The chat transcript. Can we sell the chat transcript be shared with the recording? It's a really good idea. We didn't actually do it for ML in the physical world, where we were also doing this. But I think we could, particularly if we perhaps put it on the mole, because I think people are, haven't necessarily accepted that their questions are going to be shared publicly, and I'm a bit nervous about that. So we'll have a think about that, because I want people to feel they can ask anything on the chat. So if it's there with names, that undermines that a bit. But maybe we can think about how to do that. Yeah, I've saved it in the Tish. That's not a problem. It's like if we share it, then it sort of effectively starts becoming public, and it would be nice to allow people to sort of not feel that their questions are shared. I mean, maybe an edited version of it is the right thing. I don't know. Ferenc and Nick and I can think. Yes, precisely.
Otherwise, yeah.
Would be... We will think about this. Do it in a way that. And if you have concerns if you've asked any questions and you really have concerns about it, then also just let us know.
Well, and also that's partly the point in the Reddit forum, because by creating a forum like that is public, and if you want to be anonymous on it, you can just go ahead and use it. So you see there's a few different ways you can ask questions depending on what you're comfortable with. I mean, it's always the way that some people are happy to have their questions public, other people aren't. And so we're trying to just give you a few different avenues to discuss. So if you like the chat, let's get something similar going on the Reddit forum. So perhaps if you feel the answers weren't accurate enough, or we didn't have enough time to get to something, or something occurs to you now, get it on the Reddit forum. And then we can have the type of discussion we were having on the chat, but on the Reddit forum as well. Does that make sense?
One thing I wanted to say, closing this, is there were questions about PyTorch. That PyTorch is we expect people to use it. I actually think that if you want to play around with these different mode and reverse mode automatic differentiation, which I highly recommend because I think it's pretty fun, different framework called JAX, J-A-X, that does it a lot more transparently. So in PyTorch, everything is hidden behind easy functions, so you don't have to think about what's going on under the hood, whereas JAX, everything is exposed. So it's very clear that you're running forward mode and reverse mode and so on.
Ferenc, is that also true of Autograd, which is sometimes, I know is slower, but it's sometimes...
I don't think Autograd has forward mode.
Okay.
I'm not sure it does.
But that's a great point on JAX. I have to jump to another call, so I'm going to stop the recording. I don't know, Ferenc, if you're happy to stay on, I can make you host.
Yeah, okay.
If I'm going to make the recording, will basically be from the start until this point. It takes a while to process. Please email me if there's I said something that you don't want in there, like I mentioned that you asked a question.
Before you leave, Neil, can you save the recording?
Yeah, no, I know that's all being done my end. Yeah, so that's what I'm just saying. But I'll go through a process of just dumping it on YouTube, right? So basically, if there's anything that I said in there that you don't want on YouTube, like I mentioned your name, you don't want your name to be mentioned, let me know, because otherwise, it will be on there within the next 2 hours. Okay, so just send me an email straight away. You can do that privately. Okay, sound good. Well, I'm going to make Ferenc the host with my magical power. And then drop off.
Oh, yeah.
Thanks, everyone. Thanks, Ferenc. Great. I enjoyed it.
Are there any more questions?